Welcome to the Blue Waters webinar. I'm Scott Lathrop with the Blue Waters Project at the National Center for Supercomputing Applications at the University of Illinois. It's our pleasure today to welcome Jeff Carver, Professor of Computer Science at the University of Alabama. The title of his presentation is What We Have Learned About Using Software Engineering Practices in Scientific Software. Thank you for joining us today, Jeff, and I'll turn it over to you.
All right, thank you. Welcome everybody to this webinar. I would imagine that many or most of you who are attending this have developed software of some kind, probably most of you in a scientific or an engineering context. So hopefully some of the things that I talk about today will be familiar to you, and maybe there's some areas that you want to consider for future work. What I want to talk about today, I've been working with the scientific software engineering community for about a decade or more in various formats. And so in the presentation today, I'm going to describe some of the previous work that we have done, some of the things that we have found, some of our ongoing research, and some potential opportunities for collaboration. So throughout this presentation, I'm going to start with an overview of a couple of surveys that we've done over the previous few years to get some insight into what's going on in the community. Then I'm going to describe a series of case studies of large scientific or engineering projects that we have some key lessons learned. Then I'm going to talk about a workshop series that I've been involved in for the last number of years that's been quite interesting. And then finally, I'm going to close with some direct interactions that myself and my students have had with scientific or engineering projects to give you some ideas of things that we might think about in the future. So with that, I'm going to talk very briefly about a couple of surveys that we did of scientific and engineering developers. I'm going to just give you a very brief snapshot. There's a much longer description in some other papers if you're interested in that. The first survey that we did, we sent it out to a group of people and we asked them a number of questions. And the things that I'm going to hit on today, first one is we asked them their own belief of their sufficiency of their own software engineering knowledge. And what we found was in response to that, almost everybody said that they personally had sufficient software engineering knowledge to develop the scientific or engineering software that they did, that they created. Interestingly, while they personally thought they had enough value, as you move further and further away, when we asked them about their team and we asked them about the community in general, they were less and less confident that people had more knowledge. So either we found the best people or people tend to be overconfident of their own abilities. We also identified an interesting distinction between research code and production code. So that is research code primarily written for the individual or the individual's team to do their science or engineering versus production code, which would be more like library type things that were written for other people to use. And obviously there's some things that sit in the middle. And one of the more interesting results, which led us into our second survey, is that people reported that they encountered 4 key problems when developing software. So the first one was having to do rework. The second one, not surprisingly, was dealing with issues related to performance. Then regression, so that is problems happening when they make a change or fix something, you break something else. And then lastly, forgetting to fix bugs that were not tracked. So they realized that there was a problem but forgot to track it and then forgot to fix it. So given this, we created a second survey where we tried to follow up on some of these things. And again, we sent this to a broad computational audience. We had about 150 responses. And what we did is we took the problems in the previous survey and we asked about some specific software engineering practices that are related to those problems. We didn't tell them which problem related to which practice. We just asked about a number of practices and asked people how familiar they were with them, how much they used them, etc. And what we found was the level of usage varied among those practices. But one thing we did find, because one of the issues that will show up again later is that there's a lot of times a terminology problem. So the first thing we did is we listed a practice, we defined it, and we asked the respondents whether they agreed with our definition to make sure we were talking about the same things. And generally they did agree with our definitions, and we used those definitions for the rest of the survey. And so, like I said, there's a lot more details that could be talked about, but these are the specific practices that we asked about. And in the paper that I have referenced there, if you want to read more, you can see how these practices map to those 4 key problems identified in the first survey. We have practices related to each one of the problems. And what you can see in this graph is that we have personal familiarity, how relevant it is to their work, and how much they use each practice. And the different symbols represent whether they were primarily writing research code, primarily writing production code, or things in the middle. And again, a couple of quick high-level observations. Not surprisingly, the people who were writing production code tended to find the software engineering practices to be more relevant and more useful than those who were writing research code, because of the fact that other people were going to use this. Some of these things became more important. But you can see across the spectrum of practices, some are more common and more used, and some are less common and less used. But again, every one of these relates to one of the problems that people mentioned in the first survey. So our goal was kind of to say, well, people said they have these problems. People also said they have sufficient software engineering knowledge, but they're not aware of some of the practices that might help with the problems that they said were there. So that was kind of an interesting insight into what was going on. As I said, a lot more could be said about these, but for the sake of covering other things, I'm going to move forward and talk kind of briefly about some case studies that we've done. And these case studies were done a few years back, so some of the findings may be slightly different now if we redid these case studies, but we still think that they're pretty relevant. So what our goal was in doing these case studies was to support scientific and engineering developers by just trying to understand what it is that they were doing, gathering some information about what was effective and what was ineffective in their practices, both to help their team, but also to be able to share this with others by understanding and documenting the software development practices that were happening. And then, as I said, giving direct feedback to those teams as well as sharing it with others. So what I'm showing here is just a very quick overview of the projects that we did case studies on. I'm not going to go through the details of the case study process, but the basic idea was we sent them a survey, asked them about a number of software development issues and practices that they may or may not use, and then we followed that up with an on-site interview with the team. So this was both a survey and an interview. What I'm showing you here was just to give you an idea that the application domain, the length of the projects, the size of the projects, the languages, the target hardware, there was lots of variation. It obviously doesn't cover the entire space, but it's not one particular type of project. And so what I'm going to do in the next few minutes is talk about some of the lessons learned from these projects. And the reason for showing this chart is to show that there is some diversity in these projects, and the lessons learned did not come from just one particular case study. There were things that we saw across studies. So as I said, you could look at this chart and see if the project that you work on may look very different than these, and so some of the lessons learned may not apply to your project given the differences. But at least you know the context here. So I'm going to walk through a few lessons learned. Again, we have a paper that has a lot more in them, but I'm going to hit a few of the high-level ones. And just for a little brevity, I've got a couple of Dilbert cartoons scattered throughout here to help us illustrate these points. And so here's the first one. I'll pause for a minute and let you read it. So in this lesson learned, we're going to talk a little bit about validation and verification. Again, things may not be quite this bad, but it does kind of illustrate the point that as we looked across these projects, the level of validation and verification varied both in formality and also in completeness. So for example, some people focused only on looking at the core algorithm. Some people focused on the user interaction. Some people focused on both of those. It also varied in the amount of code that was tested. And finally, it varied on whether the people that were doing the testing were dedicated testers, whether they were end users, whether there was some combination of the two. So there was really a lot of variation in this practice. And one of the other things that was interesting was whether testing or verification and validation was required by the sponsor. In many cases, people told us that they would like to do more, but we're not given the budget or we're not given the schedule by their sponsor to actually do these things. And so some of it was a sponsor issue, some of it was other things. And one other thing that became obvious was that some of the existing techniques, when I say existing, I mean those that we in the traditional business IT software engineering world use, a lot of those may not be useful in a scientific or engineering or high performance computing domain because of some of the particular issues. So let me give you an example of a quote from one of the people in our case study. That kind of illustrates the issue. That V&V is very hard because it is hard to come up with good test cases. So another quote, I've tried to position Condor, which was just one of the code names for the project, to a place where it is kind of like your trusty calculator. It's an easy tool to use, but unlike your calculator, it's only 90% accurate. You have to understand that then that the answer you're going to get is going to have a certain level of uncertainty in it. The neat thing about it is that it's easy to get an answer in the general sense to a very difficult problem. So that's a different view on verification and validation than we might see in a more traditional software engineering context. And this is another one. We have a rule of thumb. We plot 2 lines, one from MATLAB, one from C++, and if it's close, then it's okay. Again, a very different way of defining verification and validation. And then lastly, it's an engineering judgment as to which errors are important and which ones are on the margins. So there's a lot of variation in how people view these things across these case studies. So some of the implications of this, again, as I mentioned before, the traditional software testing methods may not be sufficient, but also we need methods that not only test for correctness, but help ensure the quality and the limits of the software. When is it that this should not be used? When is it pushing it beyond the bounds that it's useful for? So with many of these lessons learned, we don't want to only have some findings, but also some suggestions and recommendations. So in this case, we suggest a couple of things. One is inspections, code review, and I'll talk about that later on with a team that actually tried to implement some of this. But this is a way to help deal with some verification and validation issues. Doing some more formal planning, thinking about regression test suites to be able to retest things once things are changed. So there's things that potentially could be done about this. So let me move on to the next one I want to talk about, and this is development goals. And by this, I mean, what is kind of the driving goal for doing the software development? And again, what we found is that multiple goals are important. Going into this, we kind of assumed that performance would be an important goal because many of these projects were developed for a supercomputer. So it's not surprising that performance was a goal. But what was interesting, and may not be surprising to all of you, was that there were other goals that were just as important, in some cases maybe even more important. Portability and maintainability competed right up there with performance because, again, a lot of the projects, if you remember from the slide I showed before, were long-lived, and so the hardware underneath them might change multiple times. And so the ability to be able to move the code from one machine to the next was a key factor in the success of these projects. So in some cases, the teams would sacrifice a bit of performance for portability or maintainability. So the success depended on that ability to be able to port. So a couple of the implications here, some of the motivations for these projects might be different for traditional IT projects, some of the things that are important there. And again, the methods that are chosen for whatever software engineering or development practices are used, they have to be aligned with the overall project goals and not just put in place because somebody thinks that they're a good idea. So that's a key factor as well. So now I'm going to talk a little bit about some of the software development methodologies, Agile versus traditional, but again, let me give you a little Dilbert cartoon here. So again, if you've used Agile methods, this is not exactly what Agile is about, but sometimes it may feel that way. So the idea here is that thinking about Agile practices, and if you're not familiar with that, I'll briefly introduce it here in a second. But what we found, at least in the projects that we talked with, was that the requirements were constantly changing as the scientific knowledge evolves. So these are research projects. Things are not fixed at the beginning. There's a series of practices in software engineering called Agile software development methods, which it's a whole family of things. And what they tend to do is they tend to be more adaptable to change. They tend to have that kind of built into the process. What they do is they favor having good people and good individual practices over having heavyweight processes and tools. And so as looking at the teams that we talked with, none of them actually said they were doing Agile, but as they described what they were doing, it fit very well with the Agile philosophy. So a lot of these teams were actually doing Agile-like things, even if it wasn't formalized. And so again, some of the implications here is that the methodologies, the practices that need to be employed for this type of software needs to be flexible. It doesn't need to be something very rigid and structured if that doesn't meet the process. And so these agile inspired approaches may be the most appropriate. Next topic, next lesson learned is about the development environments, whether it's command line or IDE or something like that. So again, let me introduce this with another Dilbert cartoon. Okay, so again, maybe this is familiar to some people. So the question here is, what do people use? Here's a quote from one of the case study respondents. And this was in response to whether they think about using IDEs or not. All of the IDEs try to impose a particular style of development on me, and I'm forced in a particular mode. So it was making somebody work in a way that they weren't necessarily comfortable with. And so again, what we found in trying to understand why many of these developers tended to prefer the command line over something that was a more graphical integrated development environment. And again, the goal here wasn't to judge one better or worse, just to understand what was going on. The developers tended to prefer the flexibility. And at least in their belief was that the IDEs imposed a lot of rigidity. And the developers also thought they were more efficient typing than navigating menus. And that may very well be true. It may also be a fact of people like to use what they know. And so we don't know exactly why this is here, but this was at least the perception. And so some of the implications, we were just trying to understand why people weren't using some of the more modern IDEs. They don't trust them because they don't trust the IDE to automatically perform a task the same way they would do it manually. And we had some quotes of people that said something to that effect. They expect greater flexibility. And like I said, people often just prefer to use what they know rather than to change. So again, this is just a quick overview of some of the lessons learned from these case studies. There's a lot more details in a more expansive paper and some more lessons learned that I've got a link or reference to that at the end if people want more about that. But I'm going to move on now and talk a little bit about this workshop series that I've been organizing with a number of other colleagues to try to bring together people. So this is the link to our website here where we have the links to all the workshops and descriptions of all those, as well as some other materials, and we're continuing to add to that site. But the goal of this workshop series is try to facilitate the interaction between software engineering researchers and developers and computational scientists and engineers. And the motivation for this workshop is that we found as we began to look around that there were people interested in the intersection of these two fields, but had trouble figuring out where it would be the best venue to publish papers and to meet people. Because if you send things like this to a software engineering conference, a lot of times you get responses of, well, that's not all that interesting because it's a niche area. And if you try to publish this in a scientific domain, they say, well, it's not all that interesting because it's not about the science, it's about the software. And so this kind of felt there was a niche here for this to fill. So what we've done is we've held this workshop at a number of different conferences. So the International Conference on Software Engineering, International Conference on Computational Science, and at Supercomputing. Most often it's been at ICSE and Supercomputing. And what's happened in this workshop is that we have papers that are presented for part of the time, and then we spend a lot of time in discussion, which is the part that people really tend to enjoy. And so over the years that we've done this, we've had a number of different discussion topics and a number of different themes emerge. And so I'm going to kind of briefly overview some of the things that we've talked about on the workshops. Some problems we have ideas for, some they're just still open questions. And so it's still an interesting process. So one is about testing. We already kind of saw that in our case studies. Trade-off between quality goals. Again, that showed up a little bit in the case study. How do we balance some of these things? What about some of the differences between research software and IT software? Communication is a big issue. A lot of times software engineers, software developers speak a different language than a scientist or an engineer might. So how do we deal with some of those communication issues? If we want to introduce some kind of a software development practice, how do we measure the impact on scientific productivity? I'll talk a little bit about that. And then what about reproducibility of results? So let me talk about a few of those in detail. If we talk about domain characteristics, and so what we found, and again, this may not be surprising to many of you, but the scientific and engineering software, the domain is very complex. It's a lot more complex than the software that a software engineer at a typical consultant or something might write. It's a much more complex problem that you need a lot more knowledge to deal with. The main focus is really on the science, and the software is almost viewed as something I have to do to get to the science, and that kind of just changes the perspective a little bit. The life cycles of these projects tend to be very long, often much longer than what we see in the business IT world. Um, and because it's research software, the investigation of something unknown introduces a type of risk that's not there if I'm building, for an example, an accounting system, that I know what it's going to do. If you're doing a research kind of software, you don't know what's going to happen. And then another issue was that the developers have some different characteristics than we see in traditional software engineering. Two things. One is that the developers tend to have a very deep knowledge of the domain. In fact, many of cases, and again, you're familiar with this, you probably need a PhD in the subject area to even understand what the software is trying to do, much less try to solve the problem. So the developers tend to have very, very deep knowledge of the domain, but lack a formal software engineering or a formal computer science background. Not that they have no background, but it didn't come through a computer science type education. And the other unique characteristic is in many cases, the developers are the main users of the software. And again, that's not the case in most traditional software engineers. So this introduces some different characteristics into the domain that we have to consider. If we think about testing, some of the things that people have talked about, and again, there's some conflicting views, which is fine because this is a discussion, people have different perspectives. But in some cases, people think that the stakes are not high enough to make testing important, meaning the software is not doing anything that's all that critical, so we don't really need to test it. But on the other hand, we had people say, yes, but if you're writing something that's safety critical, or you're writing something that the results of the software can have very, very detailed implications, then maybe the stakes are high enough. So there's a trade-off here. And so the needs do differ across domains. How do you test what's important? But one of the things that did seem to be interesting was that people said what we really need to do is we need to focus on process transparency. So even if we can't test everything, at least we can help people understand what it is that we've tested, how we've done testing, how we've not done it, so that people understand the limits and they know what they can believe and not believe. And similar to that, one of the things that became very important is that people said, what we really want to do is we want to guarantee that we don't give an incorrect output. Because the perception was that if the software produces an output, people are going to tend to believe it. And so the idea was, I would rather my software crash and not give an answer than to give the wrong answer. Because if it crashes, I know I didn't get an answer. But if it gives me an answer, I'm going to tend to believe it. And so again, this is a little bit of a different perspective than we might see in other software engineering endeavors. So there's some things about testing. Talking about communication, one of the things that we came up with as a point is that we need to eliminate the stigma associated with software engineering. And by that, I mean many people, and maybe even some of you, have been had a bad experience, let's say, with software engineers. That somebody that says they're a software engineer has walked into the office with a big book of process and dropped it on your desk and said, do all this and you'll be fine, and I'll be next door if you need me. That's not the right way for this to happen, but that's the way a lot of people have interacted with software engineers. So what we need to do, and what this workshop series is trying to do, is bring people together that don't view things that way so that we can eliminate some of that stigma. And so from the software engineer's perspective, what we need to do is we need to understand some of these constraints to the domains. We need to understand the specific problems that are present, and not just say, well, here's a solution that should work for everybody. No, what's the specific issue that's showing up? And I'm going to talk a bit more about that in some of my interactions. But also we need to learn. We don't have all the answers. We haven't written the type of complex software that we tend to see here. So again, we want to have an interaction. We want to learn. We want to make sure that we're talking about concepts and terms that are familiar, so that we're actually communicating clearly and not saying different things. And there's also a need for people with expertise in both of these domains. And this is growing. There's moves for research software engineers in various contexts that do have expertise in both areas. And so that's a good thing. From the computational side, what we've also found is that We need people to realize that there's a problem before they need help. And again, that's not surprising. That goes back to the previous thing. If I come drop a bunch of process in your face and you don't think you have a problem, you're not going to use it. It's just like we don't go to the doctor unless we have a problem. So we need to make sure that we're addressing the problems that are there. And the other thing that we need, and this is part of the ongoing work, is that we need real examples of successful interactions, successful uses of software engineering practices, so that people can look at that and say, okay, I believe that because I look like them. It worked for them. It might work for me. In terms of scientific impact, as I said, we need to be able to evaluate the impact that any kind of software engineering practice has on scientific productivity. So when I say that, evaluating impact on software productivity is easy. We can look at how many lines of code are written, things like that, but that doesn't always lead to scientific productivity. And we don't have a good answer for this. We can count publications and things like that. That may be an option. But part of the issue is you need results in a relatively short time. If you're having a team try something, in order to see if something works, you may not have time to wait for the publications to come out, which might take years. So there's a question of how do we get quick results? One is self-assessments. Again, it's more subjective than we would probably like, but if you ask people that are using a practice, do they like it? Is it helping them? That's really important, because if people don't like it and don't think it's useful, they're not going to use it. Another one that people mentioned was word of mouth. That is, if I'm using something on my team and I think it's good, I'm going to tell my friends about it. So if people are sharing their experiences, that's another potentially informal way of seeing, is something working or not? Is it having impact? Because people aren't going to share and encourage their friends to do something that they don't think is working for them. Or if they do, they won't be friends long, but hopefully they're not doing that. So again, those are some of the things that we've learned. So just to come back to the high level here, we just had an edition of this at Supercomputing last month, or earlier this month, a couple weeks ago, which was successful. We're in the process of kind of summarizing some of those results, but we just learned that we're going to have the next edition of it at the Software Engineering Conference, which will be in Gothenburg, Sweden, in the end of May in 2018. The exact date of the workshop hasn't been set yet. But if this is something that you're interested in, I encourage you to attend. We will have, we don't have the website up just yet, but it will be at this link as soon as we get it up. We will be looking for papers, short papers where people can present ideas to get discussion going, but also please consider attending even if you don't have a paper, because we have a lot of good discussion during this workshop as well. Okay, so the last bit of my presentation, I want to spend a little bit of time on giving you some examples of direct interactions that we've had with scientific and engineering projects to illustrate some of the things that I mentioned earlier in the presentation. And as I said, part of the goal here is to not just be somebody standing on the side saying, do these software engineering things and you'll be good, but it's to understand what are the real problems, to interact directly with these projects, and to try to help the projects, but also learn in the long run. So one potential methodology, one type of approach that we like to follow, which doesn't have to always be exactly this formal, but is that we start with a project team and perform a case study, which can be very informal, but the goal here is to understand, what's working well in the process, what's not working well. That would give us an idea of where it is that we might have the most impact. Then we can develop a software engineering technique or identify one, tailor one to address whatever that weakness is, then deploy it and evaluate. And that's important. It's not just here, use this, but it's evaluation. Is it working? Is it not working? Does it need further tailoring? Do we need a different approach? So again, the goal here is to be interactive with the team and not to just be a one-off kind of thing. And then by doing this repeatedly, the overall goal is to begin to synthesize this and see what we can learn across projects, not just from one individual project. But what I'm going to talk about for the next little bit are some examples of doing this. And part of the reason for presenting this is that I hope at the end that maybe there's people that are listening to this who have some interest in maybe interacting with us in the future, either on one of the topics I talk about or maybe on something else that could be beneficial to your team. So I'll come back to that at the end. But let me illustrate a couple of examples here. So the first one that I want to talk about is an example of implementing test-driven development with a team at Sandia National Labs here in the United States. So I'm going to put this picture up here that comes from our paper and just quickly summarize it. I have the reference to the paper there. You can read if you want more. But what we did is we had a student who spent a semester with a team co-located out at the Sandia facility. And this team wanted to learn test-driven development. They wanted to use it on their project. And so we said, sure, we'll come out there and we'll teach you how to do test-driven development. The student who went out there actually participated in the team. And so he became part of the team. He taught them, modeled how to do it on this project. And so some of the issues that show up, and you can see this in our process. So for those of you that aren't familiar, the idea of test-driven development is that you write test cases before you write production code. And the idea is that keeps you focused on only writing the code that you need to pass the tests. And if you only write tests for things that you really need in your project, that will keep you focused on doing the activities that you need to do. So you can see across the top, the high-level process. You write a test, it fails, then you write the code to implement that test, and then you have to refactor and clean up your code, because by doing this more bottom up, it's very easy to get messy code if you don't spend a little bit of time kind of cleaning things up. So you can see underneath there kind of the specific ideas that happen. So the issue that comes up in test-driven development in scientific projects is that test-driven development focuses on writing unit tests. And so part of the question that arises is, what is a unit test? What is an appropriate level for writing a test in these environments? And that's not always an easy case. And so in this particular situation, the way that we dealt with this is that this particular project was working with a lot of partial differential equations. And so what we did in terms of our unit tests is we developed 2 tests for each PDE. We had a test that worked on a small number of steps, and then we had a test that looked at the whole time evolution. Okay. Again, you could define those unit tests in a different way, but that's the way that we did it here. And it seemed to work out pretty well. So you can see the process. They wrote the test, then they wrote the code and continued around that loop until the code passed, and then did the refactoring step of identifying poor code, refactoring, and then pushing it up. And then also having some documentation that happened alongside. And so, again, some of the informal lessons that we learned here was that it did mitigate risk of changing requirements. So there was a customer on site that was learning and doing research, and so things were changing. This worked very well. There was a reduction in the effort, and this continuous feedback from the customer was really well implemented. So this turned out to be a very good practice in this particular team. And I would say that the student that worked on this has gone on, he's graduated, and he's continuing to work with test-driven development in scientific software and other contexts. So this is a good example of how this worked. Another example, this goes back to the idea of inspections that I mentioned earlier. We had a group of people at Oak Ridge that came to us and said, we have a team that would like to start doing code review, peer code review. And so again, the idea of peer code review is just that people on the team are reading each other's code, looking for problems. It's not necessarily a replacement for testing, it's a complement to testing. Code review often finds different types of problems than testing does. So the idea here was that this team came and said, within our team, to improve our software, we wanted to learn how to do peer code review. So I had a different student who went and spent a few months in the summer with this particular team at Oak Ridge. And so again, there's a theme here. Somebody goes and co-locates, but the student spent some time there, and he taught them the peer code review process, which again is a very informal process, but he worked with them for the first few times. He did some code review. He helped them ensure that they knew what they were doing. And then after that, the team adopted that process and continued on their own performing peer code review. So they did it. He stayed there for a little bit longer as a resource, but they kind of took it on themselves. And so from this work, we've gotten a few anecdotal benefits that the team told us after introducing this process. So the first one is that they told us that they found faults, they found problems in their code that they never would have tested for. So this is a really good result from a quality point of view. And again, part of the reason that we believe that peer review and code inspection is very useful in scientific and engineering projects is exactly this case. Testing for every particular possibility is not reasonable. It's infeasible to run all the tests. But what code review allows you to do is it allows you to read through the code, look at the algorithm, look at the things that are being implemented, and potentially find problems as in this case, that you may never have actually tested for. So again, it's not a replacement for testing, but it's a complement to testing. And we saw that in this particular case. So from the team's perspective, that was a really good benefit. From a software engineering perspective, what was really interesting was that this particular team, after they did code review, they came to us and they said, we need a coding standard. And so a coding standard is a typical software engineering practice that you write your code in a consistent way to make it readable. But as they began reviewing each other's code, they said, we're writing code in different ways and it's hard to review each other's code. And so they decided that they wanted to write their code in a similar way. Again, the reason that's interesting to me, not only is that going to be beneficial for them in peer review, but by writing their code, following a standard and making it more readable, when they have to come back to their own code months later, it's going to be much more easy to understand. And so that was a side benefit that I'm not even sure if the team realized. But this was another successful interaction in terms of that area. So those were two that we've done in the past. Couple of ongoing things that we're doing now that I'm going to talk about and then kind of wrap up from there. The first one is looking at the use of software metrics in scientific software. So software metrics have been used in more traditional software for a long time, and there's a lot of discussion and debate about which metrics are the right metrics and the wrong metrics and all that. But there's a place and a usefulness for metrics in terms of trying to understand what people are doing, what's happening, what's working, what's not working. So being able to measure things is a valuable thing. So in this particular case, what we did is we did a survey of a population of scientific software developers, and you can see the goals there. So we wanted to understand whether they knew about and or used some of the more common software engineering metrics. We wanted to understand did they think that they were useful? Whether they knew about them or used them, did they find them to be useful? And then also to gain some insight into the software process that might be affected by the way that they use metrics. And so let me just show you a few quick results from this. In terms of knowledge, we can see that it's skewed towards low knowledge. So most people were unaware of some of the more common software engineering metrics. And that doesn't necessarily mean that the people who answered the survey were bad for not knowing this. It's quite possible that some of the metrics that we put on the survey may not have been relevant, or they may just not have been exposed to them. But their knowledge of the metrics, and again, on the survey, we defined what the metrics were and asked them, did they know about these things? Their knowledge was relatively low. And again, not surprisingly, the level of usefulness or the perception of usefulness was also low. So if people don't know about the metrics, they're not going to use them. But they were, the most common answer was rarely in terms of how often they use the metrics. And another thing that we looked at as we grouped the metrics kind of by category, and so you can see we asked people, in addition to answering our questions about metrics, we asked them to give us some metrics that they might use, and we categorized them. And so you can see how many different metrics people reported, how often they knew them, how often they used them. And you can see that the ones that were used most often, again, these are not surprising. People tended to worry about code complexity, most commonly about performance, which again fits some of the things that we talked about before. And then testing shows up again. Some of the other things are a little bit less frequently used. One of the things I do want to point out, because it's a growing issue, is this idea of recognition. So we didn't ask specifically about recognition, but when we asked people to tell us some of the metrics that they knew about or used, people reported metrics that we categorize as recognition. And by recognition, I mean getting credit for doing the software work. And so there's a big move going on in the field to try to see if we can help people get recognized, not just for publishing papers, but also for the software work that they do that leads to those. So it was interesting to kind of see unsolicited that this kind of metric showed up in the response to our survey as well. One other one that we have an ongoing thing that I'm going to talk about, and then I'll wrap up from here, is also on code review. So similar to the one before, but this is not working with a direct team. in this case, again, a student spent some time actually at NCSA this summer and did some interviews and some surveys of scientific software developers that we're continuing to build upon now. But the goals here were very similar to what we've done before, but to understand the code review process that's happening in these particular teams. What are the impacts and the expectations people see from that? What are some of the barriers that people face in terms of trying to use code review? And then where are some areas for improvement? Where are some things that people would want more help in doing code review? So some of the things that we found thus far in terms of the importance of code review, what we did find is that in these particular cases, a large portion of the code is reviewed. In many cases, more than half of the code is reviewed. In a smaller number of cases, it's a lesser percentage. So overall, a large portion of the code is actually reviewed. One of the benefits, and again, this is what we know from the theoretical idea of code review. It was nice to see it show up in the surveys and interviews, that by doing code review, you're sharing expertise. So if I'm reviewing your code, I'm learning about what you're doing. And so that shared expertise actually overall improves the code quality because we're looking at other things. Similar to what I just said with the team at Oak Ridge, the importance of code review is to help enforce a consistent style and reusability so that code can be used again and again and again. Also, code review is very important and good for new contributors. So as a way for somebody to learn when they first join a team, one really good way to learn is for people to go read other people's code. They'll learn about the style. They'll learn about the different parts of the software, and also on tricky features. So things that are really complicated, it's really helpful to have other people read it. And one thing I'll back up and say in terms of good for new contributors, one reason that we always argue that code review is beneficial is that for anybody who's learned a foreign language, you always learn how to read the language before you learn how to write it or speak it. But in programming, we don't teach it that way. We learn how to write first without reading. So code review actually fits the way we think about other languages, is that you're reading, and by reading well done code, you learn how to write well. Just like by reading well written literature, you could learn how to write better. So it's an interesting thing that it showed up in the survey as being good for new contributors. And then also it saves debugging time was another reason that people gave us that code review is important. Again, likely because you're finding problems earlier, and so there's less things to debug, but it does help with that process. It wasn't all positive, though. It was important, but there's also some challenges related to scientific code review. So one of the challenges, most of the challenges relate to the level of value and importance and time given. So similar to something that I said before, people view the underlying science as more important than the code, and so it's easy to say, well, I don't have time to do the code review because that's not what's most important. So that was an issue that showed up. Another thing is code review. If code review is not something people have typically done, developers tend to be attached to the way that they've always done things, and they resist change. So I've never done code review. I don't want somebody else looking at my code. They might say bad things about it, and so I'm not going to let people do that. And again, this is understandable. And part of the issue here is that in doing code review, one of the things that you want an organization to do is get to the point where we realize that by doing code review, we're not trying to look down or insult our peers. The goal here is that we all work together so that we have better code in the project. So it's really changing the culture and the perspective that code review is not a negative thing. It's actually a positive thing that we're all working together to have better code. So but that is a challenge. And similar to kind of the first one, lack of time and qualified people to do code review is another challenge. So lack of time, lack of qualified contributors, lack of people to properly review are all challenges. And then lastly, and this is kind of more of a management type issue, I guess, but and it also goes back to the culture, is how do you get people to agree to do code review? Because again, I can very easily argue if I review your code, that's taking time away from the code that I need to be writing or something else I need to be doing. And so there is a challenge there. There is a trade-off between how much time people spend reviewing code, how much time people spend doing other things. And so obtaining reviewer agreement is a challenge. And again, we could think about ways to mitigate that as well. So with that, I'm going to kind of summarize and then let you know where we go from here. So across all the things that we've talked about so far, scientific software engineering needs are diverse. So there's lots of areas that scientific software developers self-acknowledge, just like a business or an IT developer would self-acknowledge. There's lots of areas of improvement related to software quality, related to productivity, quality, people, all kinds of things. Lots of diverse needs across the software process. And those needs are deep. Some of these problems are simple, but many of them are not simple. And so if they were simple, we would have solved them. In fact, many of the problems that can be dealt with have been. So there's things like software carpentry out there. There's different practices that people are using to deal with some of the less deep issues. But these deeper issues that get to the heart of it really require a lot more time because there's really some unique problems that don't have successful, simple solutions. Again, it's not, in many cases, it's not as simple as saying, this works for the business IT world, so you should just do it in science. It's not that simple in many cases. And so these unique problems really do cause issues. And so the successful interactions, the successful ways that we understand how to do software engineering appropriately in science requires a number of things, and I've showed you in a couple of my examples. But one is it requires time. It's not a simple thing. Like I said, in those two examples that I showed you, or actually three examples, I had a student who went and physically spent time with a team. And so it's not a simple thing. It does require time commitment of some sort. It also requires openness to new ideas. And that's both from the part of the software engineer who needs to understand what are the real problems and how can the things be applied to those problems. And it also applies to the scientific developer to be open to maybe trying something that they haven't tried before. And so there's a trade-off here on both sides. And so with that, I want to wrap up. There's a Twitter you can follow there. There's my email address. If you are working on a scientific software project or an engineering project, if you are interested in learning more about some of the things that I've talked about, if you're interested in collaborating, if you've got a software development problem that you would like us to look at or make suggestions on, please feel free to get in touch with me. And also, if you're interested in the workshop series, please go take a look at the seforscience.org website. You can learn about the workshop that we're going to do at ICSE, but also we hope to do another one at Supercomputing if that's a more common venue for you. Hopefully we'll have another one there next year. So with that, I'll close and see if I don't know if there are any questions on the Slack account or not, but I'll stop here.
Well, thank you, Jeff. I've posted asking if there are any questions. There haven't been any, although Ronnie's been making some comments along the way, which are good. He said that the test should fail before you write the code and it should pass afterwards. And yes. He said the literature comparison also extends to studying master's work. It's done in games, literature, and many disciplines. Computer science, not so much. We do have a question from someone here in the audience.
Okay.
So this is Roland Haas. Just a question. Do you have any tips on how to best use these tools if you have a distributed set of developers that are not all, say, in the same working group in the same room, but at different universities, maybe on different continents?
Which particular tools are you talking about?
Say, if you want to do the code review, or if you wanted to do having a coding standard, well, I guess coding standard not so much, but code review, for example, or...
So yes, so for code review specifically, in terms of open source projects, code review has become very common, very much used in open source projects. And so many of them have tools that work well with the particular environment you're mentioning, because in open source projects, people are not co-located, so they're distributed. And so there are tools out there. One particular one that I'm familiar with is called Gerrit, that works with a Git repository, but there's other ones as well. And what these allow you to do is actually do your code review in line. And so you open up the portion of code that you're reviewing, and the reviewer can actually comment right in line in the code, and then the author can read that and respond to that. So they can kind of have a discussion right there. It's asynchronous, so it doesn't have to be real time, but it does support the distributed nature of teams like that. So yes, in that particular case, there are tools that are out there. And again, I think being that the more traditional software engineering world is also becoming more distributed outside of open source, but including open source, there are probably more and more solutions that are going to be applicable to distributed teams like that.
Okay. I think your case studies are particularly enlightening. You mentioned sending students out to help with teams. How much of that can happen either from your group or other groups? Any comment on that?
Again, it's probably been the most successful way that we have had those interactions so far. And the particular cases that we have been able to do were, I mean, somewhat opportunistic. I mean, we have a little bit of funding that supports the students, but also in other cases, the organization where the student went had some funding to support them. So it's kind of got to be a commitment on both sides, that it wasn't something that I just sent a student and say, go find something to work with. But there was already some interest on both sides. So yeah, it does take some commitment to do. I'm not sure how else to phrase that.
Nope, understood. We don't have any other questions at this point. So I think we'll stop at this point and say thank you very much, Jeff, for a very exciting presentation. Hopefully people will follow up on the references you provided. With that, this is the end of the webinar series for this calendar year. We'll be announcing a new series of webinars in 2018. So we look forward to your participation in the future seminar series. Please do complete the survey when we send it out, and the final edited video will be posted very shortly. With that, thank you very much, Jeff, and thanks to our audience.